Welcome to this explainer for the Foundry by Forge College. I am so pumped to have you here because today we are stepping straight into the engineering lab. We're rolling out the blueprints to actually test what we learned about sharding strategies in our previous lesson. Taking those abstract theoretical concepts about moving data across the Solana network and building a concrete, measurable simulation. We want to see the numbers, we want to see where things break, and we absolutely want to prove exactly how network speed optimization actually behaves under pressure. Okay, let's dive right into our experiment blueprint. We've got 6 exact steps to hit today. The sharding trade-off, building the simulation lab, slicing the payload, simulating network chaos, putting it back together, and finally, analyzing the results. So let's kick things off with section 1, the sharding trade-off, speed versus overhead. Think about trying to mail an entire house to a friend. You obviously wouldn't just hand the whole building to the mail carrier, right? Sending massive chunks of data across a network all at once is just as impossible. It completely clogs the pipes, and if one tiny thing goes wrong, boom, you have to resend the entire house. Instead, we use our fundamental unit, the shard. A shard is just a small, manageable fragment of a larger data payload, literally like an individual brick of that dismantled house. But here's the core trade-off. Single bricks let thousands of separate delivery trucks transmit in parallel for incredible speed. But the overhead? It's massive. You've got to label every single brick and write an enormous instruction manual to rebuild it perfectly. So smaller shards mean way more parallelism, but heavily increased overhead. Moving right along to section 2, building the simulation lab, our Python apparatus. To really measure that speed versus overhead trade-off without dealing with the actual, highly unpredictable internet, we're constructing a local simulation using Python's asynchronous primitives. This is our testing machinery. The blueprint lifecycle of our lab looks like this. We're going to code 4 exact functions. First, we partition the data. We break it all up. Second, we simulate the transfer by injecting fake delays. Third, we reassemble those shards on the receiving end. And fourth, we verify the integrity, just to make absolutely sure our data isn't corrupted. All right, section 3, slicing the payload. Basically, how to break a house. Before we can send anything at all, we have to decide exactly how we want to chop up our in-memory byte payload. And we have 2 primary methods for this. The contiguous strategy slices the data into neat, near-equal sequential chunks, kind of like slicing a loaf of bread. On the flip side, the round-robin strategy distributes bytes non-contiguously. It deals them out one by one into separate piles, exactly like dealing a deck of cards to players. And this brilliantly illustrates a key architectural choice. Contiguous slicing beautifully preserves the original byte order per shard, making it super easy to manage. Round-robin, though, it perfectly balances the byte load across all shards. But, and it's a big but, it demands a much more careful and complex reassembly order on the other side. Next up, section 4, simulating network chaos, throwing data right into the void. Okay, so we've sliced our data and now we're sending it into our simulated network void, using Python to inject some serious chaos. Our first variable in all this chaos is latency jitter. This is the random variance in network delay for each individual shard. Think of jitter like our delivery driver just had way too much coffee. They don't take a straight logical path, they take random, unpredictable, erratic detours. So one brick arrives in 10 milliseconds, but the next identical brick takes 50 milliseconds. It is pure simulated unpredictability. Our second variable is the concurrency limit. This is the maximum number of simultaneous transfers allowed by the network or the node. Imagine you've got 100 delivery trucks ready to go, but the highway? It only has 2 lanes. Your concurrency limit is exactly how many trucks you're allowed to put on that highway at once before a massive traffic jam completely ruins your parallel speed. So, bringing it together, here is our control panel, our lab notebook dials, if you will. We can tweak the shard count. More pieces mean higher potential parallelism, but you guessed it, more reassembly overhead. We can tweak latency and jitter to simulate really bad network weather. And we can tweak concurrency to throttle our parallel streams. By adjusting these specific parameters, we can reveal the exact queuing effects and actually find the breaking points of our parallel speed. Which brings us to section 5, putting it back together, catching and rebuilding. The bricks have flown through our chaotic network. They're arriving out of order, they're delayed, they're completely jumbled. Now we're on the receiving end, and we must put this whole thing back together. Here are our reassembly mechanics. First, we catch the return shards. Second, and listen, this is absolutely crucial, we must sort them by their integer ID. If you accidentally sort them as strings, shard 10 is going to end up placed before shard 2, and suddenly your house is built inside out. Third, we concatenate the bytes. And finally, we bring in our ultimate structural inspector, the SHA-256 hash. We hash the original data, we hash the reassembled data, and we compare them side by side. And let me tell you, when everything goes right, when your sorting logic is flawless and no data is lost, your script spits out, honestly, the most satisfying string of text a developer can see in a lab experiment. Integrity_OK equals true. The hashes perfectly match. Our reassembly logic works, and the house is standing strong. Now for the fun part. Section 6, analyzing the results. What did we actually learn? When we measure transfer durations under full concurrency, meaning, hey, the highway has unlimited lanes, we see something truly beautiful. As we bump up the shard count from 2 to 8 to 64, the transfer duration drops significantly. The parallelism is actually working. We're sending smaller chunks all at once. But notice the curve here. Eventually, the overhead of managing 64 separate connections and the CPU scheduling, it starts to eat into those gains, and we hit diminishing returns. So the really crucial point is what happens when we restrict that highway. If we throttle our concurrency down to just 2, meaning only 2 shards can transfer at a time, the results completely flip. Suddenly, having 64 shards is an absolute nightmare. Massive queuing happens. The shards are just piling up waiting for their turn, and the speed benefits of high shard counts completely evaporate. Concurrency ceilings are, without a doubt, the ultimate gating factor for throughput. Let's wrap this up and summarize our core takeaways. Number 1, granularity is a strict trade-off. Smaller shards give you incredible parallel potential, but they charge you a heavy tax in sequencing overhead. Number 2, concurrency limits absolutely govern your actual throughput. You only get parallel speed if the network actually allows simultaneous streams. And number 3, when dealing with our highly caffeinated delivery driver, high jitter, looking at the average latency is super dangerous. Why? Because it severely underestimates the absolute worst-case delivery times that hold up your entire reassembly process. This simulation perfectly empowers us to turn our gut intuition about turbine-style sharding into verifiable, hard numbers. Which leaves us with a real head-scratcher of a critical problem. If high jitter means our average latency is essentially lying to us, how on earth do we design a data distribution network that survives those absolute worst-case delivery delays? We have to somehow handle tail latency. I want you to sit with that provocative thought for a bit, because that is exactly the puzzle we're going to solve in our next explainer. Until then, keep experimenting. And don't forget to visit forge.college to dive deeper into advanced Solana concepts, access our full learning programs, and explore way more fascinating Web3 topics. See you in the lab next time.